No way. That's what's nice about class. We can oh, it drops out.
Yeah, I would divide to 3.
How would you even drop out of the class? Would you just go to like your advisor?
Higher one.
Get me out of.
I'm peacing out in this class.
That's okay.
Why? No, I'm not.
That's what you're telling me to say. I'm peacing.
Yeah.
Maybe not. Maybe just unfortunately for me, there's no possible way we can have to
I'm at a 60, so I'm at a D, and I feel like if I really try, I could possibly.
probably just a little -1.
But I.
Yeah. The 4 of them, or the -1 isn't square root.
Oh. We should get.
Yeah. It's yeah. So it's outside.
Yeah.
Okay. I just want to make sure.
And then I have to. Isabel's like, I would.
Yeah, I would say
Time to make a graph. We're gonna stay. I had to have this done by 12, and I didn't think I'd see that right either. And I went into the office, and he's like, "You're gonna be fine." And it was funny. And then I showed him that problem balance. So then he showed me how to do it. So he's awesome. He's a really good word. So tomorrow we'll be meeting during the hours, and he's just gonna give me a bunch of practice problems with the sections that I'm having problems with. It's starting to normalize it, but this morning my back hurt so bad that it was like tears. Like, that's not bad. But I was like, oh, I can just like I down.
I don't want to random guess this weekend.
I threatened.
And it didn't. Did you talk to your professor? Like, yeah, I didn't know the text not more than once.
No,
Absolutely. They should have warned you.
I just want to know what I did. We're still working on this.
Because that's so stupid.
I changed my hand, it was like $50.
Around by your hands.
Yeah.
Like I circled one, and then I erased it.
Well, you know, it's take a different so later, more experienced. And Elizabeth's teacher. Then I went to the and the guy like washed her, did her nails. And
Where did you get this?
I said, did she ever offer to break you? Oh, it's not like shave it.
All right, good morning. Are there any questions?
How was your weekend?
Yeah, it was good, thank you. They got a Halloween trick-or-treating thing. All right, so what I'm going to do is I'll pass back exams with the note that the second exam historically is always the hardest. So if your score is lower than you're hoping for, that's normal. The second exam is a really hard one. The good news is the third exam and the fourth exam get progressively easier. And the final exam is just a repeat of the first 4. I just take questions from each of the 4 exams. So if you can demonstrate that you figured out what happened and your score goes up, that's good evidence for moving up a grade. Yeah, Cameron. Thank you. Yes, sorry. Let's get into the details. They're not exactly the same, but if the question was, what's the formula or how many hydrogens are there in 2-butanol on exam 2, then the question is going to be 2-pentanol on the final exam. So let me pass those back. Exam corrections are worth 20% of what you missed, to reflect the fact that the exam is a little bit harder. 20% of what you missed. I would like to get those corrections from you before you leave on Thursday. This Thursday begins another 2-week sequence using a technique called high performance liquid chromatography. So please make sure your group signs up for a slot on either this Thursday or next Thursday. If you are going to show up and do your experimental time this Thursday, make sure you've done the reading and have your group's 10 questions ready to go. Otherwise, I'll see you next Thursday. The other thing for this investigation is you need to bring a caffeinated beverage. Caffeinated beverage. I prefer that it's diet, and that's mostly because the sugar makes things sticky, and if there's a spill, it gets kind of messy. So if you could bring a diet caffeinated beverage with you on this Thursday or next Thursday, whichever week your group wants to go. And it can be anything. It could be kind of a soda product. It could be a energy drink. It could be coffee, tea, whatever you want to check. Bring it with you, and we'll check it for caffeine content. Let me pass those exams back to you.
I'm gonna buy one second. Do you guys want like a guide?
Mine was pretty high.
Yeah, it's a good question. We are down a few, yes.
Like permanently or just?
Can't actually comment on any one individual, but I think a number of them are just for today.
Yeah, it does. It has 114 milligrams.
That's pretty intense.
I don't know.
Hiking or your fly fishing.
So if you have questions that you want to get answered today, feel free to hang out at the end of class. I'll be happy to get questions answered. Exam corrections due before I see you, before you leave on Thursday. So what I want to do is orient you towards the next unit. And the reason why the next unit is easier than the second unit is you've already done pretty much all of the calculations so far in lab. The third unit looks at counting atoms and keeping track of the number of atoms. And in particular, we're looking at this unit we call the mole as our way of counting atoms. The two main ways that we're going to get into and out of moles, you've already done. It's mass and it's molarity. Now we'll come up against a third way of getting into and out of moles for dealing with gases in the fourth unit. But for now, those are our primary means of getting into and out of moles. From the textbooks, we're working in chapters 6 and 7. What I want to do is kind of give you a big picture overview. I'm going to start off in the middle, and I'm going to work my way outwards from the middle. We can relate the chemical quantities of any two substances, provided we have a balanced equation connecting the two. Now, as part of chapter 7, we'll actually talk about how we write equations. How do we predict what's going to happen in the course of a reaction? And there are 3 types of reactions that I'll introduce you to. We refer to them as acid-base reactions, reduction oxidation reactions, and precipitation reactions. But the gist of it is there are certain rules for each of those 3. But ultimately, what we're trying to do is get to the ratios. How much of this for how much of that? And for most chemical equations, they work out to pretty simple whole number ratios. You've already run into a couple of them. It's either 1 to 1 or 1 to 2 in most cases. Occasionally, you'll see a 2 to 3, maybe a 3 to 4. Every so often, like a 2 to 5 or a 3 to 7 or something. But those are pretty few and far between. There are a couple different ways we get into and out of moles. The most common one is for a pure substance, we use the mass. 1 mole equals number of grams listed on the periodic table. And that's true whether we're coming or going. 1 mole equals the number of grams on the periodic table. Really what changes is the way we write the conversion factor. If we're trying to go into moles, we put 1 mole on top and the number of grams from the periodic table on the bottom. If we're trying to get out of moles, we put 1 mole on the bottom and the number of grams from the periodic table on top. So that'll work for any substance as long as we know it's the pure substance. We know how many grams of sodium chloride table salt we have. If we know how many grams of ethanol, even if it's a liquid, as long as it's the pure liquid. If we know how many grams of helium, even as a gas, this still works. The catch is lots of substances come to us as mixtures. The most common type of mixture is a solution, usually things in the liquid state. For dealing with solutions, we have to use the concept of molarity. Moles per liter. Molarity equals moles per liter. And so what we're doing is we're using this algebraic relationship. The 2 main ways we deal with this is either to solve for the number of moles, which is equal to molarity times liters. That'll get us into moles. And then typically we're either figuring out what the concentration is. Once we know the number of moles, we can divide by the volume to figure out the molarity. Y'all did that with the bleach. Or we could figure out the volume required once we know the molarity. Moles divided by molarity. Now, kind of foreshadowing where we're going to go in the 4th unit. We can deal with gases using something called the ideal gas law. So I'm going to write the ideal gas law out. I don't want you to do anything with it. I'm just letting you know it's out there. It's kind of coming for us, but it's really not that bad. Pressure times volume equals number of moles times a constant times the temperature. It allows us to relate volume to the number of moles and adjust for the fact that gases depend on what's going on with the pressure and the temperature. The other thing is that anytime we rearrange the chemical bonds during the course of a reaction, there's energy involved. And the energy is tied directly to the number of moles of material reacting. So anytime we burn methane, anytime we condense water, anytime we do something to the substance, to the molecules, atoms in a substance, we're going to change the bonding arrangement. And there's energy involved. And the energy depends directly on how many bonds are broken or made. And so we'll develop a relationships, conversion factors between how much energy and how many particles and how much energy. So this is out of chapter 8. This is out of chapter 9. solutions. That's out of chapter 7. And then our mass relationships. That's out of chapter 6. Now, generically, I refer to this as the mole map, just a collection of all the conversion factors that we look at in the 3rd unit and moving on to the 4th unit. And essentially everything here, except for the details of how we write equations, which we have to go over, everything here you've already done. And everything here is this is everything that's on the exam calculation wise. So up front, you know a little bit more about what you're getting into than when we started the 2nd unit talking about bonding, particularly in terms of what carbon is capable of. Questions about the big picture? All right, I'm gonna clear the board unless there are any questions. I want to jump right into it. Show you kind of a big picture kind of question. Methane reacts with oxygen to produce carbon dioxide and water. Now, we refer to this as a type of reduction oxidation reaction. But specifically, it belongs to a subset we refer to as combustion reactions. In a combustion reaction, we're always taking fuel plus oxygen and making carbon dioxide and water. Fuel plus oxygen makes carbon dioxide and water. We refer to as a reduction oxidation reaction because if we look at how the electrons are distributed, the oxygen starts off with no extra electrons. And yet in both the carbon dioxide and the water, it ends up with a -2 charge. We say oxidation number. The only way it could get more negative is if the carbon and the hydrogen ends up more positive. And so we say the carbon and hydrogen have lost electrons, the oxygen's gained electrons. The process of oxygen gaining those electrons, we refer to as reduction. Its charge is being reduced. It is getting more negative. It is being reduced. The process of something getting more positive, something losing electrons, we refer to that as oxidation. And we'll talk about reduction and oxidation in detail. It's just kind of a foreshadowing and introduction to it. The equation is not balanced. I've got 4 hydrogens on the left, only 2 hydrogens on the right. I've got to double up on my hydrogens. That also doubles up on my oxygens. I've got 2 oxygens here, 2 oxygens here. I need to put a big 2 out front here. You can't change the little numbers because of unit 2. Unit 2 is all about the atoms coming together, and they have to come together in certain ratios to address their electronic needs. How many electrons they came in with, trying to get to the octet. You got to have the right number of atoms. But once you have the right number of atoms to build a particular compound, you can adjust how many, the total number of molecules of that substance. That's legitimate. We're just reflecting what nature is doing. So for us in chapter 6, this reads as 1 mole of methane will react with 2 moles of oxygen to make 1 mole of carbon dioxide and 2 moles of water. Now, as a practical matter, this methane's a big deal. Methane's price has gone up dramatically over the last couple of months. That is good. That is good news for the state of Wyoming. We are a major exporter of methane. That methane, however, comes with some caveats, and one of the big challenges is that it itself is a powerful greenhouse gas. The CH bonds have an intense IR absorbance, even more intense than carbon dioxide. The only reason why carbon dioxide is a bigger concern is because there's more of it. In the Earth's atmosphere, we're putting out more carbon dioxide and already started out with some carbon dioxide. Methane is not something that exists normally in large concentrations in the Earth's atmosphere. The main currently the main reason why methane's in the atmosphere is because of pipes leaking. When you have 150 million Americans connected to a natural gas pipeline, even tiny leaks begin to add up. And there are some naturally occurring leaks, particularly in Russia's Siberia. There's a large section of permafrost that's beginning to thaw because of increased global temperatures, and that's releasing microbially generated methane. So it's a big deal. And in terms of energy generation, electricity, house heating, this molecule is a big player for our modern society. If I have 100 grams of methane, I can work out how much of any other substance is involved. So if I want to, I could turn that into moles. Every 1 mole of methane has a mass of 16 grams. I could figure out how much carbon dioxide is involved. 1 mole of carbon dioxide for every 1 mole of methane. Now it seems kind of silly to multiply 1 and divide by 1. But the point is, in any chemical relationship, we don't know what the relationship is until we go and look at the equation. And so we have this 1/1 here as a way of confirming to ourselves and to anybody who happens to look at our work, you know what, we checked the equation. We made sure it was 1/1. Now, math-wise, it means we can pretty much skip over this. We don't have to enter this. We don't have to multiply by 1 and divide by 1 on the calculator. Same number. But we have to have the conversion there to make sure that we've checked the equation. If I want to come back out of moles for carbon dioxide, is 44 grams per mole. Calculator out. 100 divided by 16 times 1 divided by 1 times 44. 275 grams of carbon dioxide. Into moles, between moles, out of moles. Now, the way we get into moles and out of moles may differ depending on whether we're dealing with a pure substance we can weigh out versus a mixture where you have to do the whole molarity business. We're always going to get into moles, between moles, out of moles whenever we're relating 2 different substances. Questions on any of the 3 conversion factors used? So this time, I want you to try it. How many grams of water could I make from 100 grams of methane? How many grams of water could I make? I'll give you a minute head start. See how far you get. Into moles, between moles, out of moles. So if you're still working, you can finish up and check what I've got up front. The first conversion factor is exactly the same. It's still methane. Methane will always and forever be in our system of measurement in this universe, 16 grams per mole. But the second conversion factor changes because I'm not asking about the carbon dioxide anymore. I'm asking about the water. And the water has a big 2 in front of it. That means 2 moles of water. When we go into moles, we always use 1 mole. Because at that point, we actually haven't even gone to the equation to check out the relationship. We're just focusing on that substance. Periodic table, we always look up 1 mole worth of that material just for convenience. Big 2 shows up right here. There's no number in front of the methane, so we get to assume a 1. That number shows up here. 2-to-1 ratio. Whatever substance I'm trying to find out about goes on top. Whatever substance I started with goes on the bottom, and the numbers come from the balanced equation. And the only time the coefficients, we call them, the big numbers in front, the only time the coefficients show up in our conversions is when we're relating 2 substances. If I'm going into moles or out of moles, the equation doesn't show up yet. The last conversion factor is the same structure. It's grams over 1 mole, but the number differs because the substance differs. 100 divided by 16 times 2 times 18, 225 grams of water. Any questions on those reconversions? In moles, between moles, out of moles. Now, you can always stop at any one of the conversion factors. You could stop after the first one and say, hey, I figured out how many moles there are, moles of methane. I could stop after the second one. I could figure out how many moles of water. But in terms of what we measure down the lab, it's usually mass. So we try to go all the way from grams of one thing to grams of another. If I add these guys together, 275 plus 225, 0, carry the 1, it's 10, carry the 1. There's 500 grams of stuff altogether, 500 grams of stuff. I only started out with 100 grams of methane. I start out with 100 grams of methane and I end up with 500 grams of stuff. Where did the other 400 grams come from? Where?
Atmosphere.
The atmosphere, specifically in the form of
Oxygen.
oxygen. That's right. Well, let's check it out. 100 grams of methane. How much oxygen do you need? Actually do the calculation. It should come out to be 400. Let's check it out. I'll give you a minute head start. 100 grams of methane. How many grams of oxygen? What do you guess? First conversion factor, same as all the others. We're just trying to get into moles for methane, 16 grams per mole. Second conversion factor changes because we're asking about the oxygen. You can relate any 2 substances in the equation. Doesn't matter whether on the left-hand side of the arrow or the right-hand side of the arrow. The only thing that changes are the verbs that we use to describe what's going on. So we would say, how many grams of carbon dioxide are produced, released, made But for oxygen, we'd say how many grams of oxygen are used, consumed, involved, something that implies that it's getting used up. The important thing is that I use the numbers from the balanced equation. 2 oxygens for every 1 methane, 2 oxygens for every 1 methane. And for oxygen is 32 grams per mole. 100 divided by 16 times 2 times 32. Sure enough, 400 grams. Questions?
Is that 16 grams of methane? Or 10?
It's
That's supposed to be a
That's
6.
why I'm
Yeah.
getting the wrong
I
number.
get that too.
Okay, that's why.
Thank you for helping me clear that up.
You're
16
good.
grams, not 10.
No judgment. That's why I was like, why am I
Other questions? Yeah, Brent.
So when we have the 2 moles of O2 and the 2 moles of H2O and the 1 mole of CO2, that's just based on the equation we have above.
That it. Yep, that's it. Exactly. Most chemical equations are 1-to-1 or 1-to-2 relationships. Yeah.
So every time you combust, methane is the same.
What's that? Say it again.
It'll have the same reactants every time you combust.
Now, I'm going to kind of dig into this a little deeper. Every time we burn methane, this is the goal. This is what we're aiming for, but it requires that we have the right amount of oxygen relative to the methane. It turns out if you don't have enough oxygen, methane can do other things. There are other bonds it can form. In particular, instead of carbon dioxide and water, you can get carbon monoxide. And so carbon monoxide is a valid Lewis structure. It's a way carbon and oxygen can get together, but it doesn't release as much energy as forming the carbon dioxide and water. So it's our goal is to make sure we get enough oxygen in there. As a practical matter, that carbon monoxide is incredibly toxic on inhalation. It's odorless, tasteless. The only way you can detect it is typically using a sensor of some kind. And it's a serious concern because we'd like to be able to burn methane to heat water, to heat our homes. And if there's not a sufficient air intake, then immediately the concern is the carbon monoxide that's produced. But for our purposes, we're always going to assume when I say combustion, we mean complete combustion. Because if it's incomplete combustion, the possibilities actually get kind of complicated. You get the carbon monoxide, but you also get carbon forming little chains, making soot molecules that are really undefined in terms of their composition. So it becomes very difficult to write a good balanced equation for it. I don't know if that was kind of where the question was headed or not, but are we okay?
Yeah, you answered my question.
So I want to dig a little bit into that formula methane, CH4. Every 1 mole has a mass of 16 grams. Now, of that 16 grams, we've got 1 mole of carbon, which is 12 grams, and we've got 4 moles of hydrogen atoms, for a total of 4 grams. So the 16 is because of carbon and because of hydrogen. And specifically out of that 12, 4 grams, sorry, out of that 16, out of the 16, 4 grams is due to hydrogen. If we divide this out, multiply by 100, we get a percentage. We say the percent of mass due to hydrogen would be 4 divided by 16 times 100, 25%. 25% of the methane's mass is due to hydrogen. 12 out of 16 times 100% of mass due to carbon, that's equal to 75%. 25% of the methane's mass is due to hydrogen. 75% is due to carbon. This is what we refer to as a percent composition. can do this for any substance. So C3H8. 1 mole is equal to, actually, I'll let you guys work this out. You go ahead and, if you don't have a periodic table, go ahead and get one out or look one up. If you have a periodic table handy, if you don't know these masses, you get to know them over the next couple class periods. How much does 1 mole of propane add up to?
Or-
44 grams. Good job. So what I'm having us do is work out how much of that 44 is due to carbon and how much of that 44 is due to hydrogen. So take a second, try to work out what percent of propane's mass is due to carbon and what percent of propane's mass is due to hydrogen. I'll give you a 30-second head start. Grams out of 44 is due to hydrogen. So we'd say this is 18.2% hydrogen by mass. And 36 out of 44 grams times 100. That works out to 81.8% by mass carbon. All we're doing is we're taking the part divided by the whole. How many grams of each element compared to the grams of the overall quantity for the same number, for a fixed number of particles. So now here's what I want to do. I want to turn it around the other way. I'm going to clear out the stuff up top here. Use propane as our example. Pretend you can't see this part. Just bear with me. Pretend you can't see this part. All you know are the percentages. Can we get back to the original formula? Can we figure out what the ratio is of carbons to hydrogens? And the answer is yes, thanks to the periodic table. Which is 18.2% hydrogen and 81.8% carbon. What I could do is pick any mass I want and figure out how many grams I want to work with. I'm going to assume I've got 100 grams worth of stuff. The reason why I assume 100% is because of what percentage means. If I have 18.2% of 100, what does that equal to? 0.2. I could do any mass I want, but if I do 25 grams, now I've got to take 18.2% of 25 grams, and it just adds a little bit extra hassle. So if I assume 100 grams, I must have 18.2 grams of hydrogen for every 81.8 grams of carbon. Now the catch is our molecular formulas work based on how many, not how heavy. So here comes the mole concept. I don't want to know how heavy the hydrogens are. I want to know how many there are. Every 1 mole of hydrogen atoms has a mass of 1 gram. How do I know that? The periodic table tells me so. There must be 18.2 moles of hydrogen. I want to know how many moles of carbon. Every 1 mole of carbon atoms has a mass of 12 grams of carbon atoms. 1.8 divided by 12, 6.8 moles of carbon. And so now I can write a formula. C 6.8, H 18.2, right? That's the ratio. That's how many carbons are to how many hydrogens. Why does that look weird?
That's.
Yeah, you can't have a decimal atom.
Parts of
You
it.
can't cleave an atom into pieces and actually have it be an intact thing. It's going to go off and the protons and neutrons are going to try to find another atomic arrangement to be stable. So this is a mathematical artifact. It's just happens to be based on the way we've assumed 100 grams. We've got 6.8 moles for every 18.2 moles. We'd like a whole number relationship, so we're going to divide through by the smallest number. So 6.8 divided by 6.8, that's 1. I don't need to write the number 1, just a symbol will do. 18.2 divided by 6.8. I get H2.67. I still don't have a whole number for the hydrogen. So here's the idea. If I divide through by the smallest number, most times, most compounds, you'll end up with whole number relationships. But if you don't end up with a whole number relationship right off the start, it's telling you there's an odd number relationship in the formula. All right, so 0.67. What's the way we say 0.67 in fractions?
2/3.
Thought I heard it.
2/3.
2/3. 2/3. Good job. So in fractions, it'd be 2/3. So it's like saying carbon, hydrogen, 2 and 2/3. Another way to write that would be carbon, hydrogen, 2 times 3 is 6, 8/3. If I triple everything, C3H8, I get my whole number relationship. But this molecule must have 3 carbons for every 8 hydrogens, which is why it didn't come out to a nice whole number relationship. But there's an odd number here. That 3 is what messed us up. And that is the same formula we started with, C3H8. Now, if I wasn't sure if I'd done this right, I could still just work out the percent composition. Carbon is, let's see here, 36 out of 44. Hydrogen is 8 out of 44. I'd get the same percentages. It must be the same compound. But if you divide through by the smallest number and still don't get a whole number relationship, there must be an odd number relationship. You'll have to scale it up a little bit until you hit the exact odd number relationship. This is what we call the molecular formula. Because it matches the actual molecule that we're talking about. It's also referred to as the empirical formula in this case. The empirical formula is the simplest whole number ratio. I'll write that out again over here. The empirical formula simplest whole number ratio. The molecular formula is the actual ratio for that substance. Empirical is the simplest. Molecular is the actual. Questions on anything up here before I clear the board? Let me give you an example of this molecular empirical business. Molecular formula for glucose is C6H12O6. The empirical formula, if I divide through by 6, CH2O. Empirical formula is just the simplest ratio of elements for that compound. It does not necessarily actually match, doesn't necessarily match the actual formula. It's just the simplest ratio. In this case, it has some consequences for us. Glucose belongs to a class of compounds called carbohydrates. Why are they called carbohydrates? Because they have one carbon for every one water. Carbohydrate. Now that speaks to the origin of carbohydrates. All the carbohydrates that we eat, rice, pasta, whatever, any carbohydrate we eat is directly from photosynthesis. So the wheat that went into the flour, the starch that's in that wheat was put together by the plant, taking the carbon from carbon dioxide and nailing it together with a water molecule. That at its heart is photosynthesis. Ripping the carbon out of carbon dioxide, taking the OH out of water, joining them together. I want to turn our attention back to calculations involving a chemical reaction. And I'll focus on this one. Hydrogen plus oxygen to make water. I'll give you a second to try balancing the equation. The equation is not balanced currently. Okay, to balance this equation, you'll need to put a big two in front of the water. That'll get the oxygens fixed, but that doubles up your hydrogen, so you'll need to put a big 2 out in front of the hydrogen. So we'd say 2 moles of hydrogen for every 1 mole of oxygen will give you 2 moles of water. I should note that you also get a bunch of energy out of this. So let's say we mix some hydrogen and oxygen together. How do we figure out what's going to happen? We've got some hydrogen, we've got some oxygen. We're trying to figure out how much water we can make. In our household, this is the classic hot dog and bun problem. We check in the meat store, and we got a certain number of hot dogs, and we check up on the other shelf of the fridge, and we try to figure out how many buns we have left. Now it gets a little complicated because a couple members of our family actually don't like to have the hot dog buns, but that's a whole separate issue. There's a stoichiometry, a relationship between hot dogs and buns. 1 hot dog for 1 bun, 1-to-1 ratio. And so if I look at the hot dogs, and I've got 5 hot dogs, and I look at the buns, and I've got 4 buns, I've got a problem. I've got a limiting reactor. Poor Morgan's being like, why is he talking about hot dogs and buns?
It's a great.
There's a certain number of hot dogs and a certain number of buns, and there's a relationship between them, and we got to figure out which one's going to run out first. The same thing's true with chemical substances. The catch is that unlike hot dogs and buns, where we're actually counting them directly, we measure out substances using beakers and balances. And so we get quantities that can get into moles, but we have to do that relationship. So we measure out the hydrogen and the oxygen based on mass, or based on molarity, or based on volume of gas. But at some point we have to do a comparison. We have to figure out which one of these things is running out first. So I'm going to share with you 2 approaches. Your textbook actually has a little flow chart in chapter 6. I'd prefer you not follow the flow chart. I prefer you kind of understand what we're looking at, which is, are you going to run out of one of the 2 ingredients? Based on the number of particles, are one of the 2 ingredients going to run out? So the 2 approaches I'm going to share with you, I refer to them. These are not officially recognized chemical terms. They're just what I've come up with over the years. You've got the do it twice method. And you've got the comparison of moles method. And you don't even have to remember these two terms I've come up with. I'm just using it to organize what I'm sharing with you here. Do it twice method or comparison moles method. I'm gonna clear out the top section here so I have a little bit of room to work. Actually, the comparison moles method, I'll move right over here. I like the do it twice method because it describes it pretty adequately. We're going to do the problem twice. We're going to say 50 grams of hydrogen. How many grams of water can you make? Every 1 mole of hydrogen, 2 grams of hydrogen. And then you can make 2 moles of water, or 2 moles of hydrogen. And then you can get 18 grams of water for every 1 mole of water. And do it again for the oxygen. Another 30 seconds or so. Into moles, between moles, out of moles. In the first case with hydrogen, it's 2 grams per mole for the hydrogen and 2 waters for every 2 hydrogens. The last step is going to be the same in both cases because we're figuring out how much water can be made. 50 grams of oxygen. We have to change the bottom of the fraction because oxygen's heavier, 32 grams per mole of molecular oxygen. 2 moles of water for every 1 mole of oxygen. Last conversion factor is at 18 grams per mole. So 50 divided by 2 times 2 divided by 2 times 18. Based on the hydrogen, we should be able to make 450 grams of water. Based on the oxygen, 50 divided by 32 times 2 times 18. Only 56.25 grams of water. The reason why we're getting 2 different answers is because this is 2 different numbers of particles. One of these runs out first. And in the do it twice method, whichever one is less product, that tells you this is your limiting quantity. Say limiting reactant or limiting reagent, it's the limiting ingredient. Even though the masses are the same, they are not the same number of particles. Oxygen particles are 16 times as heavy as hydrogen particles. So if you've got the same mass, you automatically start off with less oxygen to work with in terms of the number of particles. They're going to run out first. Now, the other thing we can do with this is once we realize we've got 100 grams of stuff and you only make 56.25 grams of water, where's the rest of the stuff? So we say lost. I want to, it's, no. We're not doing a nuclear process. We're not converting matter into energy through chemical means. It's the other, let's see here. So it's 40 43.75 grams of stuff that's gone missing. Where'd it go? Well, what went in the atmosphere?
Hydrogen.
The hydrogen, right? So it doesn't matter so much where it goes, but it is accounted for by the hydrogen. So 100 grams minus 56.25 grams, we've got 43.75 grams of hydrogen excess or unused. This is our excess reactant. And 43.75, we really didn't use much. We only used about 7 grams of hydrogen. Now we could actually do that calculation. You could start with 50 grams of oxygen, work your way through to how many grams of hydrogen get used. But we can get there by looking at the results as well. So the other approach, I think a lot of people are quite happy with the do it twice method. But the comparison moles method is equally valid. I just want to point it out to you. 50 grams of hydrogen. Every 1 mole of hydrogen is 2 grams. So we essentially stop here. We don't go any further. 50 divided by 2 is 25 moles of hydrogen. Because what we're doing is we're figuring out how many of each. We're actually figuring out how many particles are present. 50 grams of oxygen. Every 1 mole is 32 grams. 50 divided by 32, 1.56 moles. And then I compare them. The balanced equation is saying 2 to 1. Do I have a 2 to 1 ratio? If I don't have exactly a 2 to 1 ratio, in what way is it off? In what way is it not a 2 to 1 ratio? And 25 compared to 1.5, I have got way too much hydrogen. And I have definitely not enough oxygen. What that means is once I've done the comparison of moles, then I just have to do this calculation. I just have to do the second one. In other words, instead of doing the whole thing twice, I just compare the number of moles and then only do it the one time based on the limiting quantity. Works. Both approaches work. You don't have to use, you can use either one. Doesn't matter which one. Questions? All right, so I want to show you what a limiting reactant situation looks like. But to do that, I have to go get the hydrogen and the oxygen. So I'm going to go get that. Before I go get that, I'm going to set you up with a problem. Questions before I erase what I got here? We're going to stick with the hydrogen oxygen. I like the hydrogen oxygen reaction for a bunch of reasons. From the context of the calculations, I like it because it's got 2 to 1 ratios in it. So you have to look at the equation to make sure you've got the right ratio. So if I have 200 grams of oxygen and 20 grams of hydrogen, what mass of water is produced? What'll happen from here is I'm going to run down, I'm going to get a container that's filled with hydrogen gas and oxygen gas, and we'll light it up. It will make a loud pop bang noise when all said and done. So if you're uncomfortable with loud noises, just letting you know, feel free to hang out in the hallway if that would make you feel more comfortable. But I will be back in just a couple minutes with that. You guys crunch the numbers.
Oh, wait. Just do
That's the spirit.
Yeah, I think so.
Go to the spreadsheet. this would just.
I thought I had this once in the bag. 16. Yep, knew I got 31.
I should have a page already.
Yeah, so mine's.
More sodium than this.
I got that from.
I'm feeling with me.
Is that the
Oh. The last, the Louis Dog.
Number 28.
It's also
The last one. I got it wrong. I thought we did it, so I'll answer you Well, I knew it was like the second to last one.
Why didn't it go through to 20? It was working already. Who took it?
I'm gonna show you, I started now. Clearly, we're not on the same wavelength.
Are you putting it as control or to stir and genome stir?
No.
This is taking him a while.
Like almost exact same thing as.
I like pop
All
tarts
right.
because we're not healthy.
So let me set up what I've got here. Let me tell you what I've got here. I've got an orange juice can that has a hole in the bottom and a hole in the top. I've got tape covering both holes. I just filled the can with hydrogen, completely filled with hydrogen, no oxygen. What's going to happen is I'm going to pop the top off the tape, take the tape off the top, take the tape off the bottom, and light the can, right? That'll start the reaction between hydrogen and oxygen, but there's no oxygen inside the can, so the hydrogen's got to come out of the can and react with the oxygen. You won't see a big flame because it's a really happens right at the opening here. But as hydrogen leaves the can, air is coming in the can. When the ratio gets to be 2 to 1, particles of hydrogen to particles of oxygen, then the flame can drop into the can all at once. There won't be a lot of noise, so I'm asking you to cover your ears. I never know.
Right when he starts, I never know. Did you think when he first walked in, it was like a
That's the first time I've ever gotten a basket over here in the sink. That was pretty awesome.
There's a dent in the ceiling now.
Oh, yeah, it's Joyce' brethren over there. Yes.
They went up to the I missed
It doesn't go off at once is because there is no hydrogen, sorry, there's no oxygen inside the can. There's a limiting reactant problem. Once enough oxygen comes in the can, then the flame can drop in once you get to the right ratio. And there have been a couple times where I forget to take the tape off the bottom. And then it completely fizzles. It's got to wait so long that the hydrogen begins to get out too fast and it never kind of drops back in. I've also tried it where if you lift the can up with like some dowel rods or something, it goes way faster because the airflow in becomes much faster. So it all comes down to how quickly do you get that oxygen into the can. It also means you could step in, as long as you had a source of oxygen to keep you going, you could step into a room full of hydrogen you wouldn't be able to light a match unless it's one of those special strike matches that has the oxidation reaction built into it. You have to have both ingredients and they have to be in the ratio that you're looking for. So my question to you guys is, since you had a couple minutes, which one of these two is limiting?
Honestly, hydrogen.
The hydrogen, yeah, sorry, I wasn't sure.
It's the hydrogen.
Hydrogen's limiting. Let's check it. I'm going to do the comparison to moles method. 200 grams of oxygen times 1 mole over 32 grams. That's 6.25 moles. 20 grams of hydrogen. Every 1 mole is 2 grams. That's working out to 10 moles of hydrogen. My question is that a 2-to-1 ratio? 2-to-1 ratio? No, it is not a 2-to-1 ratio. And in fact, as I think about it, if I were to have twice as much hydrogen, I should have 12.5 moles. I do not have 12.5 moles. This is limiting. Based on that limiting quantity, 2 grams of hydrogen, every 1 mole is 2 grams, 2 moles of water for every 2 moles of hydrogen. That's 18 grams of water for every 1 mole of water. Based on the limiting quantity, the 2's cancel. 20 divided by 2 is the same as 10. 10 times 18, 180 grams of water would be possible. 180 grams of water versus 220 grams of stuff that I started with. That tells me there must be 40 grams of oxygen that go unused. If I'm making 180 grams of water and only 200, if I'm making 180 grams of water and I had 220 grams worth of stuff to start with, that means I have to have 40 grams that don't get used, and that must be the unused oxygen. 40 grams of oxygen go unused. Questions? For Thursday, read through the HPLC packet. If your group is meeting me on Thursday, get your 10 questions together and bring in a caffeinated beverage. Otherwise, I'll see you for the instrumentation time next week. Everybody shows up Thursday at 1 p.m. for lab though. Thank you all.
I can find it.
Yeah.
Where was it?
Oh, that's okay. Yeah. Yeah. That's okay. Here, if you hold on a second, I'll do it right back. You skipped a page. 2 pages. So your call, I can give you a 7 out of 10 now, or you can bring it back finished on Thursday. I'll get you 10 out of 10.
Thank you.
All right.
I'll just give her 7 out of 10.
You know what, Charlotte?
Yeah, I do, dude. I'm almost too excited.
Where's the sign up sheet at for the?
Oh, it's underneath the, I need to post that again, don't I? Let me go ahead. It's the same one that you went to previously, but I'll go ahead and recopy it here.
Oh, that's what.
So if you go to the announcement from the last one,
I found it. We can do it.
Let's just do it this week.
I think if it makes more sense for me to put it, I think I'll put it out as, and if you guys know where, can you guys get to it?
Yeah.
Okay, all right. I'll send out another announcement tomorrow or something.
Yeah.